Thank you. First of all, thank you for the invitation. I'd like to speak about elastic elements in track, and mainly about the question how this influences track costs, and it's total track costs as seen over the service life. We have some challenges, although the system works quite properly, but we have the challenge that we have mixed traffic. We have very dense transport systems like you have here. We run in some double track sections 320 trains a day, which gives very, very limited time for maintenance. And this time is shrinking and shrinking, and of course the costs climb up very impressively. So the only way to combine this availability and the maintainability is to get a track which is more sustainable. And for my understanding, sustainability has two phases. The one phase is the technical one, and that's the precondition of all that. And then we have to evaluate it if we can really do it, if it's worth to do it. So if we want to speak about a sustainable system in technique, we have to think on the quality behavior. Already in some presentations it was mentioned that there is some kind of E-function of deterioration, which is of course because of the dynamics. So we need to understand quality behavior, and then we can do life cycle costing, as the understanding and the prediction of quality of track is the precondition to do really life cycle costing. This was implemented at Austrian Railways from the year 2000 to 2002. All the regulations turned to life cycle based regulations in investment and in maintenance. We call this together life cycle management. It started with a very, very old experience that a good track behaves quite nicely, a poor one not. As I'm academic, we fiddle around with words, we change this sentence to the next sentence, which says absolutely the same. Degradation depends on the present quality level. However, if you give this sentence to a mathematician, he sees a differential equation, which you can solve, because that's change of quality is constant, and that gives a very simple quality function. So that's just transposing experience to mathematics. This function is quite important, I think, as it describes the total behavior of track, not the components behavior. And it contains of the initial quality, that means it contains of investment, and it contains of maintenance, because that's the E with the power of pt. T is time, P is the rate of deterioration. First of all, we learn we cannot split investment and maintenance. Second, this is describing nearly the life cycle cost, just nearly, because we always take into consideration the costs of, we call it operational hindrances. In fact, that's the costs of non-availability due to track work executed, or due to track work not executed and then running slow. These costs are taken into account as well. So we can use this technical function as a function for the economic description, as well as it should picture, the economics must picture the technical situation. What's the background of that? And that's a very nice background. We have the data from the Austrian Federal Railways. It's not a very big network, but a dense used network, 4,000 kilometers of main track. So that is all the track where really big traffic happens. I have the data of track type, track age, components, all recording cars. We run the recording car between 3 and 4 times a year. Then the maintenance executed, the transport, the alignment, and so on. That's nice data. But what makes this data really nice is that we have got these data in a time sequence from 2001 to now. And that gives appearance about behavior. So if this is whatsoever quality figure or measurement car figure, we look it over time, we look how it changes. And this gave us that formula as well, now in a data-based situation. But we have to take into account that this rate of deterioration, the B, is very, very much related to all the boundary conditions. Traffic load, subsoil, dewatering as the biggest impact, but also, of course, all types of superstructure. And we can do analysis for that and getting some pictures like this, so we see how it deteriorates. There was a maintenance and further on and further on. We discussed which parameters we have to take into account. That's the most important ones. There are more. So it's of course traffic load. It is track number, although the track doesn't know that there's a twin on the side, but the costs do know it, and so we have to take it into account. Then it's the rail profile, steel grade, sleeper type, radii, rails. We do practically not have jointed rails anymore, and it's subsoil condition. A lot of possible variation. A lot of these possible variations are not normal. You would not run 60,000 tons a day on 49 kilo rails and jointed track. So that's a lot of combinations are not reality. 300 remains, 80 we needed to describe the network. So we see our network as a sequence of different standard elements. That's done for track and turnouts, of course. The next thing was to think, what is the life-limiting components in track? It's not the rails. The rails can be changed quite easily. It's not the sleepers. In normal, even the concrete sleepers have a nice service life, except we put it in water, that's not so liked. But it is enough, and the concrete sleepers have still enough service life, more than track. Remaining the ballast. We also can change ballast, but that's so costly that normally this is the reason for the economics to end service life. So either it is because the ballast is going round and it doesn't become stable, that doesn't keep stable anymore, or it's because the ballast bed is filled with fines and you cannot damp it anymore, or it has no positive effect anymore, or very little. That is the basics on all our calculations, all our life cycle strategies which we build up for the Austrian railways. So we have the one deterioration function which describes entire track behavior, and this gives a limit for service life. And of course we have then to add all the components, because might be that we have to change the one or the other component in between. So we have to do the prognosis for all components, but the main thing is we first need a description of entire track. Track is not just a by chance mixture of a lot of components, it's a civil engineering building. Unfortunately, from my knowledge, it's the only civil engineering building where it happens from time to time that we believe we can build a civil engineering building without basement. That gives then remarkable problems. So we put a lot of time into looking into graphs for and analysis for subsoil behavior and things like that. That is executed in Austria now since 2011, that all the major projects come and are tested for the optimal service life. What I would like to show here, and that's the headline of today, is the elastic elements, and we proved under sleeper pads in Austria. The test started in the beginning of 2000. In 2007, it became general regulation to use it for concrete sleepers. First of all, it was for the higher loads, because you get the best benefits there, and now it's spread to all concrete sleepers. There is a limit still, so we don't use it for concrete sleepers which carry less than 10,000 tons a day, but we do not have concrete sleepers with less than 10,000 tons a day, so because that's the limit to use concrete sleepers, so we use it practically everywhere. What was the reason for that? And everywhere in track and in turnout. And what was the reason? Of course, concrete sleepers are a very good option. If you think on the world record in 55, after one of the world record run, the track was not usable for the second train. In 2007, or 2006, the last world record from SNCF, after this record, it was just opened. track was just opened because it was stable, it was mechanized installing, it was mechanized maintenance, and it has a constant side resistance. So we need concrete sleepers for the high side resistance. They are cheaper, minimum in Austria and in main Europe, they are cheaper than wooden sleepers. It's the other way around in the US. They have a very low maintenance demand, yes, but if a problem you cannot maintain a lot of, so we have to think when to change rail beds and things like that. They have a long service life, normally longer than track, but they have a big problem. And this big problem is the high deterioration of ballast. And this is a technical problem, and it is a very big economic problem, as this is exactly the component which is limiting our service life. So the idea was how to better that. And the reason for that problem was that we have just roughly 3 to 5% of contact area between concrete sleeper and ballast. If we use the dynamic track stabilizing, we can double the figure. But that's still just 10%. And if you take the calculation of track, you use much more contact area in calculation than in reality. So the idea was to use an elastic element more or less to distribute the load better. First of all, this additional elasticity distributes the load to more sleepers, taking away the peak load under the sleeper. And it gets more contact area between sleeper and ballast. Or to say it in another word, we try to get the benefits from the wooden sleepers towards the concrete ones. I took here some figures which were the testing results. Without dynamic track stabilizing, wooden sleeper has up to 10% contact area. Using dynamic, you can roughly double the figure. The concrete sleeper is quite poor in that. This is a picture where you see the contact points. And it's only some contact points. And when we go for concrete with under sleeper pads, we come up with the dynamic stabilizing up to 35%. That gives a big increase in area, a big decrease in stresses in ballast. Suddenly ballast starts to work as ballast and not just as a single fourth pass. This reduces initial settlement because you have more stones in contact from the beginning. If we have reduction in the initial settlement, we have reduction of the differences in the initial settlement between the different sleepers as this settlement is random. And therefore, we can increase the initial quality. That's an expectation. And if that happens, we should decrease the deterioration rate. It was at that time also expectation, just that's telling about the stresses and about the contact area. Of course, if you increase the contact area, the stresses go down in the ballast. What I would like to show you is that graph. That is an analysis of something between 600 and 1,000 kilometers of track. It's 60,000 sections, which are compared track with under sleeper pads and track without. What you see here is the initial quality measured in standard deviation. So in a normal track in Austria, we realize a standard deviation of 0.5 millimeter on a gliding mean of 100 meter length. This is a limit which is accepted. If this limit is overridden, the company gets some problems. We could reduce that initial quality from 0.5 to 0.3, which is not that much, but which is huge. Because if you think on an E function of behavior, and you can increase the beginning point, you can increase the flat part of the E function, and that's time, that's service life. And more impressive is the rate of deterioration. It was 0.14, again measured in standard deviation, 0.14, and it halved. It is reduced dramatically. We looked at in tamping demand. That's again the 60,000 samples. We have the sections with under sleeper pads and the sections without under sleeper pads. And this is not expectation. The last two slides are not are not expectations. That's test results. We could spread the cycle of tamping by that factor. So we go for tamping roughly after the double of the years, without loss of quality. Otherwise, we would not benefit in service life. The only expectation still is that about service life itself. You see, the test started here. In 2007, it came into the regulation. As you know, when it's written down in the regulation, it needs some time until it runs through the organization. But let's say from 2009 onwards, we have mainly the sleepers are used with under sleeper pads. We still install a short part of wooden sleepers for special sections, and we still install some concrete sleepers without pad. That's only if we do a very short section or a single sleeper exchange. We do not want to have the point of with under sleeper pad without and jumping from that. That gives single failures. But you see, it's quite well implemented. And what does it mean in cost? And within that figure, it's all the proof and examples for maintenance, just the relation between maintenance and service life, which we could figure out on a lot of analysis, is still an calculation. Of course, we did never change this track, it is too new. But if we look to a normal reference track and we see that's annual average costs seen over service life, the total ones, and it's built up the biggest portion up to 50%. In turnouts, it's more than 50, it's 60 to 70%. That's just depreciation. So track is expensive and keeps long. That's the good thing on that. Then we have maintenance cost, which is the reference is regarding to a track used by 150 trains a day, one track. So we have maintenance cost, which is in about the same like the costs we put to the operators in disturbing them. Of course, if you go to branch line, the blue bar disappears. Let's say, in bad words, if no train coming, no train is delayed. But in main lines, it's really an important part. Doing this prognosis, so the maintenance is already proven, doing the prognosis, we can reduce the annual average cost down to 68%. That gives internal rates of return for the additional investment of 20%. Imagine we invest 5% more, half the maintenance, and increase roughly 25% service life. So that's beautiful. We did the same thing on turnouts, and we expected more savings in the turnouts as they are more sensible. It was not like that. It is in absolute figures, because this 100% is roughly 11 times higher than that 100%. So in absolute figures it's more, but in relatively it's less. The reason is only if you can save the ballast in track, you can increase service life, and you do not need to do big new maintenance. When you increase the service life in a turnout for 20%, you most likely have a frog exchange or some expensive maintenance additionally. But still, it gives beautiful savings. And to show you that that's not just in Austria, in 2013, the French got it into their regulations only for TGV lines. They made a 10 years test, of course, not telling that to anybody, but it was a test of 10 years, 1 kilometer. Here you see the standard deviation. You see all the red marks are tamping actions The green ones are grinding actions. By the way, you see if you combine it, it gets the best. That's another strategy which is already implemented in Austria. We put it together. On the test section with under sleeper pads, they did less work. This doesn't tell anything, but if you know or if you see that the change of standard deviation, so the behavior in that case, I think the graph really becomes quite impressive. Thank you.